Machine learning is currently one of the sought-after skill sets in the global economy, but for most beginners, the entry point is far from clear. Most existing roadmaps are notoriously dense and difficult to navigate. You sit down to learn, and suddenly you're staring at a mountain of concepts: gradient descent, eigenvectors, recurrent neural networks, pandas, feature scaling. It is an overwhelming volume of information to process at once. While some online tutorials promise you can master AI in 30 days, the academic reality often demands months of abstract mathematics before you ever write a single line of code. This creates a unique paralysis. You don't know if you should be opening a linear algebra textbook or just copying a Python tutorial from YouTube. Learning machine learning effectively is essentially an optimization problem of your own time. There is a constant debate over whether you actually need a math PhD to build AI, or if you can simply learn Python and figure out the mechanics as you go. This chart shows the trade-off we're dealing with: theory versus practice. Over-indexing on theory can leave you unable to build actual products, but over-indexing on code limits your ability to innovate when a standard model doesn't work. To master this field, we have to look at the exact return on investment for each phase of the roadmap. We need to balance the friction of learning with the actual reward of deployment. The first phase of this roadmap is foundational math. This chart shows where foundational math sits: high effort but high long-term impact. This involves spending weeks studying probability, calculus, and linear algebra. This study grants you a structural intuition for how AI models process massive datasets and arrive at the most probable predictions. For example, training a neural network is fundamentally an optimization problem known as gradient descent, which relies entirely on calculus and derivatives to function. The trade-off here is a massive upfront time cost. You are investing hours into abstract symbols without seeing any immediate, flashy results. Because you won't build a working model during this phase, the risk of academic burnout is high. Foundational math provides the theoretical engine for everything that follows, but it lacks the immediate gratification of a finished product. This leads to the execution phase, programming, specifically with Python. Looking back at our quadrant chart, Python and optimized libraries like Pandas, scikit-learn, and TensorFlow offer high immediate impact for a more moderate amount of effort. These libraries handle the complex mathematical operations for you, allowing you to prototype and deploy neural networks with relatively little code. However, this speed comes from abstraction. You are essentially working with a black box that hides the underlying mechanics from the user. If your model fails or outputs inaccurate data, you won't intuitively know why it happened or which parameters need to be tuned to fix it. Code makes the building process exceptionally fast, but without the mathematical foundation, debugging those systems is nearly impossible. Next is the third, and often overlooked phase of the roadmap: data engineering. This is arguably the most tedious part of the process, requiring you to format, clean, and scale raw information before it's usable. This chart shows the necessity of feature scaling. If your data includes values on a scale of 0 to 5 and others on a scale of 0 to 100, the algorithm's calculations will be skewed unless that data is normalized. Handling these details correctly leads to reliable, accurate predictive models that actually function in a real-world environment. Skipping this unglamorous step renders even the most sophisticated, mathematically perfect neural network completely useless. We then move to the final phase: evaluating models against validation data and diagnosing errors. At this stage, you'll likely encounter overfitting, where a model merely memorizes its training data rather than learning actual underlying patterns. Training an AI is a recursive process. The work is never truly finished because you are constantly monitoring for performance shifts. Correcting issues like overfitting requires a time-consuming loop of tweaking parameters and retraining the system from scratch. Enduring this iteration is the required cost of building a robust, production-ready model. Applied machine learning is an iterative cycle of testing, failing, and retraining until the results meet your specific requirements. Because the total roadmap is so vast, you should optimize your path based on your specific end goal. This decision tree shows two distinct paths for tackling the syllabus. For the practitioner, someone who needs to build apps or analyze business data quickly, prioritize Python, Pandas, and scikit-learn. You only need enough math to conceptually understand how the algorithms function. For the actual execution, you can rely entirely on the libraries. This route offers the highest immediate return on investment for developers who need practical deployment over deep academic theory. Then there is the innovator. This is for the person who wants to push the boundaries of AI, build custom architectures, or reproduce cutting-edge research papers. If that is your goal, you cannot skip the foundational math. You must be willing to pay the high upfront time cost of studying theory before you ever touch a real-world dataset. While high-level libraries have commoditized the execution of AI, the intuition behind these systems still requires mathematical rigor. Regardless of which path you choose, don't let the massive scope of the total roadmap stop your progress. Success requires picking the path that matches your immediate goals, using community datasets like Kaggle to practice, and starting your first training loop today.